Hi everyone. Just finished doing a video on integrating a cylinder to find the moment of inertia of the cylinder, and in that I'd used a dV equals 2 pi r h dr for the volume, and I explained that it's really a cylindrical shell, so it's not exactly correct in case y'all were already noticing that, but I said I might come back later and give you a video to show you why it's okay to use that formula. So that's what I'm going to do now. I have the drawing laid out in two ways, one where it's like a rectangular solid, and the other where it's actually what it is, which is a cylindrical shell. And I'm going to work out the details and show you exactly why it's okay to use 2 pi r times h times dr for that differential volume element. So let me turn on my document cam and show you. So this is the problem that we just did earlier. That was the result I got for a cylinder. And notice that would be true for a thick cylinder or for a infinitesimally thin cylinder. That would also work, but I just did for a thick cylinder. So what the volume really was is really the cylinder whose outer radius is r plus dr, and then you subtract out the cylinder whose outer radius is plain r. So the formula really is related to that, but what we did was assume it's like a rectangle. In other words, we ignored this little part right here, which has a length from here to here of 1/2 dr times pi. So, or excuse me, 2 pi times 1/2 dr, and this is the same distance from here to here is 2 pi times 1/2 dr, and that makes it more like a triangular portion. But what I pretended was that it was 2 pi r times dr times h, where h is the height. So I want to show you that that's acceptable. So this formula, as I told you, is a cylinder with the middle cylinder can't cut out. So we know the area of the volume of the cylinder is actually pi times r plus dr, that's the radius of the outer cylinder, squared, and then times h, that's the whole volume inside of this red outer line right here. So now I got to subtract the volume inside of this red inner line. So I'll say minus pi r squared times h. So if I carry this mathematics out, you can see I get pi times r squared plus r plus 2r r dr plus dr squared times h minus pi r squared times h. Now I distribute that pi and that h, I get pi r squared h plus 2 pi r dr h plus pi dr squared h minus pi r squared h. So if you see now, if you look now, you can see that this pi r squared h cancels out completely with this pi r squared h, and all I have is this 2 pi r dr times h, which is what I used as my differential volume element. And notice it differs by this quantity pi dr squared. As I told you, when you take an integral, it's a Riemann sum of little partitions, and those little partitions are set, basically have a limit acting on them to make the dr, the differentials, get infinitesimally small. So you're taking the limit as dr gets infinitesimally small. So dr is really, really small to begin with, but if you multiply dr times dr, it gets even smaller. Just try multiplying 0.001 times 0.001. If dr was 0.001, that's quite a bit bigger than 0.001 times 0.001. So this one really is able to be ignored, and that's it in a nutshell. So now you know why we have, for this type of shape, you can say dV is equal to 2 pi r dr times h. And of course I put the h before it because I wanted to make sure y'all remembered that we're integrating all that stuff. But that's why you'll see similar things with spherical shells. They'll sometimes say a spherical shell has a volume of 4/3 pi r squared, that's the surface area, and then they'll just multiply that times the thickness dr. Well, the same thing applies with that type of case, in which you'd have basically a sphere of radius r, and then you have a differential thickness right here from here to here, whose thickness is dr. So in reality, it's this big sphere. The volume is this volume of the big sphere minus the volume of the little sphere. So it should be 4/3 pi r plus dr cubed minus 4/3 pi r cubed. Well, if you want to carry this math out, you go 4/3 times pi times r squared plus 2r plus dr squared. That's just the squared, so I still have to multiply it by r plus dr, minus 4/3 pi r cubed. Okay? Space is getting kind of tight. I'll come over here and let's say 4/3 pi. Now I'm going to distribute this. I'll get r cubed when the r hits the r squared, plus 2r squared dr when the r hits that term, plus r dr squared when the r hits that term. Now I got to make the dr hit it, so it'll be plus r squared dr plus 2r dr squared plus dr cubed. Okay, that's just the first term, so I still have minus a 4/3 pi r cubed. Now I have a common factor of 4/3 pi, and here you can see that clearly this 4/3 pi r cubed is going to cancel out with that 4/3 pi r cubed. But what is left is, in fact, 4/3 pi times 2r squared dr. So that takes care of that term. Plus 4/3 pi times r dr squared. That takes care of that term. Plus 4/3 pi r squared dr. That takes care of that term. Plus 4/3 pi times 2r dr squared. Plus 4/3 pi dr cubed. So that's actual dr cubed there. Okay. Now you can see this term, 4/3 pi times r dr squared, that has a square in dr. This one has a cube in dr, so these are going to be approximately 0 compared to the dr term. So those are going to disappear. This one's going to disappear as well, because that's the same thing, about 0. So we end up getting 4/3 pi times 2r squared dr plus 4/3 pi r squared times r squared dr. So basically we have 3 times 4/3 pi r squared dr. In other words, I took this coefficient, this coefficient by itself and the non-coefficient of 1 that's imaginarily here, and added those, because the remaining parts, 4/3 pi r squared dr, 4/3 pi r squared dr, are still the same. And by doing that, I end up getting the 3's canceling out, and you get 4 pi r squared dr. So if you want to use a spherical shell, you can see that in reality, in the limit as dr approaches 0, infinitesimally small. In other words, the dr squared terms, the dr cubed terms are all going to essentially be zero, and all you're left is with 4 pi r squared dr, which is literally the surface area. The surface area of a sphere is 4 pi r squared, and then times the thickness dr. So that's why we can use that too in other cases of integrations. So hope that clears that up for you. I know that was a problem that bothered me when I took calculus, because we kept using this little thing, and I think my instructor explained it sort of like this too, but I don't remember, because at that time I don't think my brain was ready. So you might not have been ready when you encountered that in calculus as well. So hopefully this will help you.